Hello, and welcome to Homework Help for Math 2. Today we're going to be looking at Unit 1, Lesson 3, Quadratic Functions, Scott's Muscle March. We'll start with the ready section. Directions say multiply using the distributive property. And first assigned problem is number 1. So when we are multiplying a monomial by a binomial, we want to distribute that monomial to both terms in the binomial by multiplying. So when we have x times x minus 7, our first term is going to be x times x, which is x squared. And then our second term is going to be x times negative 7, which is negative 7x. And so our final answer is x squared minus 7x. For number 2, again, we're going to take our monomial. We are going to distribute it to both terms in the binomial. That means we're going to be multiplying. So 8 times x is 8x, and 8 times 3 is 24. So our final answer is 8x plus 24. Next assigned problem is number 4. So with number 4, very similar to the first two problems, this time notice that our monomial is negative. So just want to be careful that we include that negative with any multiplication that we're doing. So our first term is going to be negative 5 times x, which is negative 5x. And then our second term is going to be negative 5 times negative 4. And a negative times a negative is a positive. And then 5 times 4 is 20. So our final answer here is negative 5x plus 20. And the last problem that was assigned in this section was number 7. Same general idea. We're going to be distributing our monomial to both terms of the binomial. We're going to be multiplying. This time our first term is going to be 4x times 8x. Now we're multiplying, so that means we multiply our coefficients. All right? This is not 12x. So this is going to be 4 times 8, giving us 32. And again, we're multiplying. This is not x plus x, this is x times x. And so x times x is x squared. For our second term, we've got 4x times 10. So we multiply our coefficients, giving us 40x. So our final answer for number 7 is 32x squared plus 40x. Our next problem appears in the set section. Directions here say use first and second differences to identify the pattern in the tables as linear, quadratic, or neither. Write the recursive equation where indicated. All right. First question is number 10. So we're given a table of x and y. We have to choose between linear, quadratic, and neither. The directions told us to use the first and second differences. Even if the directions did not say to do that, we've now seen this a couple times where when we're trying to figure out the relationship, looking at the first and second differences is a good idea. So even if that was not in the directions, we would still want to do that. So looking at the first differences of our outputs, y in this case, so to go from negative 6 to negative 4, we want to add 2. To go from negative 4 to negative 2, we add 2. Negative 2 to 0, add 2. 0 to 2, add 2. 2 to 4, add 2. 4 to 6, add 2. Pretty clear pattern here. We are seeing a constant pop up in our first difference. So when you see a constant in our first difference, that tells us that we are dealing with a linear pattern. So our answer here is option A, which is linear. For the recursive equation, so even though this table This table is in terms of x and y. We've seen frequently sort of like f of x, things like that. For our answer, if you put y, that's fine, but because we are dealing with a recursive equation, our job's going to be significantly easier if we use function notation, even though the original table was not given as a function. Function notation is definitely preferred with recursive equations. So we're still going to use f of n as we have in previous lessons. And as always with a recursive equation, they refer to previous terms. So in this case, we're going to be referring to the immediately previous term, which is f of n minus 1. And with a linear function, basically we're just saying, well, what do we need to do to each previous entry in order to get the new entry? So what do we need to do to -6 to get -4? What do we need to do to -4 to get -2? Well, that's literally what the first difference is, which is 2. So every single time, we simply want to add 2 to the previous term to get the new term. That's what a linear function is, and that's what the recursive equation looks like. Now, as always with a recursive equation, we also need a starting point because it's always referring to some previous term, so we need to just sort of start somewhere. And in this case, they give us what happens when x equals 1. When x equals 1, our output is 2. So I might as well start with that one. So f of 1 gives us 2. And we just sort of treat that as our starting spot. So these are our 2 answers for number 10. Next question is number 11. Again, we want to look at the first, potentially second differences. So looking at 4 to 0, this might actually be the first one that was assigned where we're initially seeing a negative. So to go from 4 to 0, we want to subtract 4. We're going down. To go from 0 to -2, we still want to subtract, but it's actually not by as much. We want to only subtract 2 this time. Now to go from -2 to -2, we add 0 or subtract 0. However you want to write that doesn't really matter, but by default, I guess we go with addition in the absence of a reason not to. So we don't really do anything there. And then to go from -2 to 0, well, now we're increasing. So now it's +2. To go from 0 to 4, we obviously add 4. And to go from 4 to 10, we add 6. So right off the bat, not linear. Because with a linear function or a linear relationship, this first difference has to be the same number, and that is clearly not the case. So definitely not linear. Let's check out what happens with the second difference. So to go from -4 to -2, the number is less negative, right? The magnitude has decreased, but it's getting closer to 0. It's getting closer to the positive numbers. So we're adding here. We're adding 2. So -4 plus 2 gives you -2. It's less negative. And then to go from -2 to 0, well, again, we're kind of moving to the right on the number line, so we're adding 2. -2 plus 2 results in 0. The rest of this is pretty straightforward. 0 to 2, we add 2. 2 to 4, we add 2. And 4 to 6, we add 2. So here we can see that our second difference is a constant. Our first difference is following a linear pattern. It's increasing by 2 every time. And that is pretty much our understanding of a quadratic function. So our answer here is going to be B, quadratic. Okay. And for the recursive equation, again, we'll use function notation. Makes our life a little bit easier. So f of n equals f of n minus 1, that represents the previous term, And now we've seen a couple times that with a recursive equation for a quadratic function, the first part of the sort of the what follows the f of n minus 1 is we want to add the constant second difference, which in this case happens to be 2. It's all those plus 2's in the second difference, times our input, which is n. And then we need to figure out what if anything, follows this, right? Is there any sort of like maybe plus or minus, something that goes here, right? We need to just sort of double check and make sure that that kind of works for us. So again, there's a couple different ways that we can do this, but I think that probably the easiest way would be to look at two consecutive pairs here, and we could really pick any two pairs, but I'm going to just choose the simplest ones, which are 1 and 2. Why not choose those? So looking at our recursive equation, if we were to say, if we let n equal 2, excuse me, if we let n equal 2, so we're talking about this guy, then f of 2 is going to equal, looking at our recursive equation, f of 2 minus 1, so f of 1. And we have this 2 times n, but remember, we're letting n equal 2 in this case, so n becomes 2. And then we might have something at the end here that we don't know what it is, so we'll just call it d. Well, our table tells us that the output when you plug in a 2 is 4, right? Remember, this y is essentially f of x or f of n, whatever our input is. So when we plug in a 2, we get a 4. So that's what f of 2 is going to be. F of 1 is what happens when we plug in a 1, which is right there. That's 0. So f of 1 is 0. Oop, wanted that to be red. So that's 0. Plus 2 times 2 is 4, and then plus d. All right, well, 0 plus 4 is 4, and then if we subtract 4 from both sides, we end up getting 0 equals d. So it actually turns out that we don't actually need another term in our recursive equation. So I'm actually just going to erase all of that. And it turns out that that is our recursive equation, which means the only thing left that we have to do is identify our starting point, which, again, we're given what happens with 1. So let's use that. So f of 1, our sort of starting spot, is 0. And then we could determine other terms based on that starting position. Next question is 13. Again, we want to look at the first and potentially second differences. So 24 to 22, we subtract 2. 22 to 20, we subtract 2. 20 to 18, we're subtracting 2. 18 to 16, we're subtracting 2. 16 to 14, we're subtracting 2. And 14 to 12, believe it or not, we are subtracting 2. So by now, this might look familiar. We have a constant in our first difference. And that tells us, pretty much right off the bat, that we are talking about a linear function. And actually, with this problem, that's all we got to do. The pattern is A, linear. And we are not asked to come up with any sort of recursive equation here, and so we're done. Next problem is 14. First differences. So to go from 48 to 22, we subtract 26. To go from 22 to 6, we need to subtract 16. To go from 6 to 0, we subtract 6. To go from 0 to 4, we add 4. 4 to 18, we add 14, and 18 to 42, we add 24. This is not linear, because our first difference is not a constant. Let's look at the second differences. To go from negative 26 to negative 16, our number is becoming less negative. The magnitude decreases, but it's getting closer to 0, and so it's getting closer to the positive numbers. So we are adding 10 to go from negative 26 to negative 16. Likewise, negative 16 to negative 6, we're getting even closer to the positive numbers. And once again, we add 10. Negative 16 plus 10 is negative 6. To go from negative 6 to positive 4, we kind of flip over from the negatives to the positives, and those are 10 units away on the number line. We're going to the right, so we're adding 10. And then the rest of these are easy, plus 10, plus 10. And so again, we can see that our second difference is a constant. Our first difference, because our second difference is a constant, that implies that our first difference is following a linear pattern. It is increasing by 10 each time, and that is pretty much the definition of a quadratic function. And so that is our answer for 14. Next problem is problem number 16, and we are starting with some figures here. So we got figure 1, figure 2, figure 3, figure 4, and first part of this problem, 16a, is saying draw figure 5. Got a little bit of space to do that. So there's actually a couple different ways of sort of drawing this. The end result should be the same, no matter what your approach is, but sort of like how you look at this can look different, sort of the process. For me, when I look at these figures, what I see kind of right off the bat is I see two boxes that are kind of doing their own thing in every single figure, right? So in both the top right and the bottom left, we've got these two boxes that are kind of jutting out a little bit, and like they're not really changing every single time, right? You've got 1 and 1, 1 and 1, 1 and 1, 1 and 1. So those guys are kind of hanging out. So when we draw figure 5, I think it makes sense that we would expect there to be a sort of a similar top right, bottom left, for there to be this one box that's doesn't really play nicely with others. And then what we have left over every single time is we have this rectangle. Okay. So every single time we've got this rectangle, and unlike the two kind of random boxes, the rectangle is definitely increasing as the figure number increases. So with figure 1, if I look at and again, we're focusing on the rectangle now. So if I look at the rectangle and I'm looking at the horizontal distance, we'll call it the width, I guess. So that's this guy right here. Notice that in the first figure, it's 1. In the second figure, it's 2. Third figure is 3. Fourth figure is 4. Figure 1 is 1, figure 2 is 2, figure 3 is 3, figure 4 is 4. That's a pretty clear pattern. I think it's reasonable to expect that our rectangle in figure 5 is going to have a width of 5. Now looking at the height of the rectangle each time. So we'll go like that, I guess. So for figure 1, our height is 3. For figure 2, our height is 4. For figure 3, our height is 5. And for figure 4, our height is 6. Very similar pattern to the width. In fact, in some ways it is the same pattern. The only real difference is that you're starting at a different spot. So the width started at 1 and went up 1, 2, 3, 4. The height also goes up by 1. It just happens to start at 3. 3, 4, 5, 6. So it's basically the same pattern. So with figure 5, we would expect we've got our two misfit boxes, bottom left, top right, and then we've got a rectangle that is 5 boxes wide and 7 boxes high. So now we just have to draw it. So I'll start with the rectangle. We've got, let's see, let's just start by drawing quasi-arbitrary rectangle and see how far this gets us. So we want our width to be, just double checking, 5. Okay. So that means we want there to be 1, 2, 3, 4, 5. That's good. And we want our height to be, I believe it's going to be 7. Yeah, 3, 4, 5, 6, 7. All right, so our height of this rectangle is going to be 7. So we've got 1, 2, 3, 4, 5. Let's add another one. 6, 7. Let's just double check. 1, 2, 3, 4, 5, 6, 7. Good. All right, so that is a 5 by 7 rectangle. And then we can just tack on our 2 random guys right there and right there. And that is our picture for figure 5. Figure 6, predict the number of squares in figure 30. Okay, show what you did to get your prediction. All right, well, luckily they're not asking us to draw figure 30, because that sounds like a pain. So all we need to do is we just need to predict the number of squares in figure 30. So if we think about the way that we drew this, and again, you might have drawn your figure in a slightly different process. The end should be the same, but if we approach this problem the way that I drew the picture, we might be able to come up with an idea of what's going to happen with figure 30. So with figure 30, and I'll do a little bit of scratch work, maybe just like over here, I guess. This is just my own little area here. So we want what's going to happen at, figure 30. And if we think about the way that we sort of drew this rectangle, well, remember and I'll go back to the picture and just label everything. So our width, so this was in green. So this is my width of the rectangle, which is 5. And this was my height of the rectangle, which was 7. And then we got rando and rando. So if I wanted to know the total number of boxes in like figure 5, right, the one that I drew, well, I could sit here and add them all up, and I would get 37. That's fine. But much, much easier than adding up every single box would be to simply take the 7 and the 5 and multiply them. Right? So if we did 7 times 5, and then add the 2 random boxes, we get our 37. So that figure right there has 37 boxes. If you don't believe me, go ahead and count them up. You'll see that there's 37. Now with figure 30, counting up all the individual boxes, well, first of all, you'd have to sketch it, which is annoying, and then you'd have to count up the boxes, which is annoying. But we can actually come up with an answer much easier. If you think about it, in figure 30, our width is going to match the figure number. So the green number is the figure number itself. Figure 1, it was 1. Figure 2, it was 2. Figure 3, it was 3. So in figure 30, well, you could imagine that my rectangle, my sort of central rectangle here, is going to have a width of 30. Then our height, again, you think about the pattern, it went 3, 4, 5, 6, 7 for figures 1, 2, 3, 4, 5. So for figure 30, it's going to be my figure number plus 2, right? Because if you go back to the original one, right? In figure 1, it was 3. 3 is 2 more than 1. In figure 2, it was 4, which is 2 more than 2. In figure 3, it was 5, which is 2 more than 3, so on and so forth. So in figure 30, we would expect our height of our rectangle to be 30 plus 2, which happens to be 32. And then don't forget, we've got our 2 sort of random ones. 2 random boxes, bottom left and top right. Those don't really change in any sort of meaningful way. You're more than welcome to try to do this in your head, but it turns out that this is 962. 962. Right? So that's essentially our answer. And if we really want to be impressive here and sort of state our answer in a nice, maybe readable way and not just rely on a bunch of scratch work. So our prediction, it ends up being, show what you did. So our prediction is going to be 962. And our explanation is that since the figure number is, and let me go ahead and change the box size, since I'll have to do that eventually anyway, might as well just do it now. All right. So our prediction is going to be 962. Since the figure number is multiplied by the figure number plus 2, and then 2 more are added. So again, that's sort of like how I viewed this problem. If you got 962, first of all, good job. The chances of you lucking into that are pretty small. So if you got 962, but you had a different way of sort of deconstructing this figure, there's about a 99% chance that that is also correct. And there are other ways of looking at this figure. So 962, and then the way that you sort of got that can vary depending on sort of how you see this figure being constructed. C, write an explicit formula for finding the number of squares in any given figure. All right, so it's an explicit formula. So again, we're going to use function notation. So let's make this black. Okay. So again, we're going to use function notation. So f of n equals. If you think about what we did up here in our scratch work, well, what we did was we took our figure number, multiplied by our figure number plus 2, and then added 2 at the end. Well, okay, just do the same thing, but just instead of saying 30, let's use n, because it could be for any given figure, right? Not just 30, but whatever number we want. But we already did the heavy lifting, because what we're going to do is we're going to take our figure number, which is n, we're going to multiply by 2 more than n, so n plus 2, and then add the 2 that are in the top right and bottom left, and that becomes our explicit formula. And please make sure that you can see the similarity between our work that we did for part B and our answer for part C. The last problem that was assigned in this section was in the Go area, and our directions here are write the first 5 terms of the sequence. And the problem that was assigned was number 18. All right. So we're being asked to write the first 5 terms, and right off the bat, hopefully we can recognize this as a recursive, come on, recursive formula. Okay? This is a recursive formula. It is telling us that, all right, well, this is f of 0, which is fine. So that's our starting spot. We're starting term 0, essentially. We get a 24. And then the rest of this is saying, all right, from now on, once you plug in a 0 and you get 24. If you want something else, if you want the next term, so for example, f of 1, we'll take the previous term, f of 0, and subtract 5 from it. So I'll just, I guess we'll make little like placeholders here. All right, so we're looking for the first 5 terms, 1, 2, 3, 4, 5. But I'm actually going to leave space for term 0. So we'll go ahead and we'll call this, term 0, and then we'll call this term 1, term 2, term 3, term 4, and term 5. And this is going to be our answer. So we just got to figure out what goes in each of those lines, and we're done this problem. And we are told, like all recursive formulas, we need a starting spot. And we're told that f of 0, right here in the red, is 24. Then, in order to get term 1, think about what this is saying. This is saying f of 1 means f of 1 minus 1, which is 0, minus 5. Well, f of 0 is 24. They told us that. It's right there. So this thing is this thing. It's 24. So if I want f of 1, it's simply 24 minus 5, which is, drum roll, 19. If we want f of 2, again, our recursive formula says if you want f of n, take the previous term and subtract 5. So f of 2 is going to be f of 1, which we just identified as 19, subtract 5, well, it's 14. Hopefully people are starting to see a pretty clear pattern here. 24, 19, 14. We're simply subtracting 5, which might make sense because that's what this is saying. This is saying take the previous term, subtract 5. So let's just finish out the rest of this problem. 14 minus 5 is 9. 9 minus 5 is 4. And 4 minus 5 is negative 1. You're just subtracting 5 every single time. And so the first 5 terms are 19, 14, 9, 4, and 1.